This podcast will continue talking about TCP. Specifically, we're going to talk about sequence numbers and how TCP uses sequence numbers to send data. As we should recall from our studies of IP, we can send an IP datagram that contains up to the maximum transmission unit or MTU of data. So if we have a picture that's megabytes in size, and we can only send, or kilobytes in size for that matter, bigger than 1 MTU, which is normally around 1,500 bytes. We can only send 1,500 bytes at one time. How do we get this giant, gigabyte file across the network in a reliable manner? Well, the way that happens is TCP, the application will send that data down to TCP. TCP will break it up into manageable size chunks, and then it will number the data, and then it will send it, and then the other side will acknowledge it to prove that it got it, or to acknowledge that it got it. So we're going to take a 3-step process to try to understand how it works in the real world. So first, we're going to assume a simple case for the numbering of the data. And that simple case is that TCP is going to number the data. It's going to start at 0, and it's going to number each segment with a number. So in this case, I probably should have done this before I started, so you guys don't have to watch me type. Oh, that's not what I wanted. In this case, we're going to assume that this giant rectangle that I have up here is a picture or file that needs to be sent, and these tiny rectangles that I'm putting numbers on are the numbers that TCP is assigning to each piece of data, right? So let me finish segmenting my data so that I can send it in frames. How big are these segments? Well, they're no bigger than the MSS, the maximum segment size. So we have this maximum segment size idea that we talked about in a previous podcast. Well, that controls how big the segment can be. So here we go. I have my data segmented, and what I'm going to do is I'm going to take some number of these segments, put it in an IP datagram, and send it on its way. So what I'll do is I'll send 0 and I'll send 1, and I'm going to use the example like the capture file I have did. It sent 2 segments and waited for an acknowledgement. So I'm going to say, hey, here's data 0, here's data 1, and I'm going to wait. And the other side is going to respond, hey, I'm ready for data 2, because that's how the acknowledgement works in TCP. It is a forward acknowledgement. It acknowledges what the next byte of data you expect to get is. So the reason that's a good thing, say I sent 1, 2, 3, 4, 5 segments at once. I say I sent all 5 of those. If I acknowledged each segment, if I was required to acknowledge each segment, I'd have to send 5 segments back to acknowledge it. But I can acknowledge all 5 of those segments just by sending back an acknowledgement with 5. So that's the forward acknowledgement. So this is how it works. TCP breaks the data into segments, sends those segments individually. Don't close my virtual machine. Whew, that was close. Sends those segments individually numbered. These segments are not guaranteed and will likely arrive out of order. So the receiving TCP can use the sequence numbers to put them back in order. Why is it likely to arrive out of order? Well, because our IP protocol is not connection oriented. Our data can take different routes. Our data is not guaranteed to arrive, so we may have to ask for data to be resent, which TCP can handle that. So conceptually, this is what happens. The data gets numbered, it gets sent, and then it gets acknowledged by the recipient. So the last thing after the recipient gets this last segment, it's going to acknowledge 21, being like, hey, yo, I need 21, and you're going to know, oh, well, I sent everything. So that's how it works conceptually. In practice, there's 2 things that actually work differently. One, it doesn't number the segments, as in segment 0, segment 1, segment 2. It numbers the bytes of data. So this, we'll assume each of these blocks is 20 bytes long. So then this will become data 0 to 19. This will be data 20 to 39. This will be data 40 to 59. This will be data 60 to 79. I'm only going to do 2 rows. This will be data 80 to 99. This will be data 100 to 119. Is that right? Yeah. So instead of numbering these segments by the segment number, we number these segments based on the byte of data contained in that segment. So here I'm going to send, if I send this first frame, then my sequence number, here let's go now. My sequence number for this will be 0, sequence 0. For this segment, my sequence number will be 20, and for this segment, my sequence number will be 40. So my sequence number is the first byte of data contained within that segment. So, right, my first byte of data is 0, so my sequence number becomes 0. My first byte of data in this segment is 20, so my sequence number becomes 20. My first byte of data in this segment is 40, so my sequence number becomes 40. So that changed my ACKs. Up here I was ACKing 0, 1, or 2. Well, you the recipient ACKs the next byte of data it expects to receive. So should the recipient receive this frame or this segment and not get any other segments, they would ACK back 20, because 20 is the next byte of data it expects to receive. If it gets this segment and this segment both, so it got data up to 59, it would ACK back 60, because 60 is the next byte of data it expects to receive. So that's how it actually works with regard to numbering of data bytes versus numbering of the segments. It numbers the bytes of data and not the segments. And then to further complicate things, we must pick a large random initial sequence number. So instead of actually having nice, easy to understand, easy to add sequence numbers that start at 0 and count up using small numbers, we end up with a 32-bit number. Like we look over here, 28723140023, 28723140023. Hey, darn it balls, typed in the wrong place. Is that gonna work? Yeah. So here's my first byte of data. I'm going to change that to 20 so I can add easier. Here's my first byte of data, which will make my last byte of data be 28724144039. Right? So that makes my next byte of data be 287241440. Right? If my last byte is 39, my next one will be 40. Right? And if I have 20 bytes of data in here, then that's going to make my 2414059. Right? So that's my last byte of data. And then for this guy over here, I'm going to have 28724144060. And my last byte will be 28724144079. So as you can see, when we go to the real way it works, it gets a little more complex to analyze and make sense of the numbers. So it works the same way. This would be the sequence number on this segment, right? If I sent this segment to the server and the server got that segment and wanted to acknowledge that it received that segment, then the acknowledgement number would be this, which is the next segment it expects to receive. Right? So then I say I send two segments at the same time. I send this segment and I send this segment. So the last byte of data that was sent to the server would be, this number 28724144079. What would be the next byte of data that the server expects to receive? 28724144080. So it got 79. It would be acknowledging 80, saying, hey, I expect to get 80 next. So that's how it works conceptually, from easy, let's try to understand it, to, oh wait, here's how it actually works. Now let's look at our actual capture file and track down some of these sequence numbers like we're going to be doing in the lab. So we're going to start, in this case, at frame number, let's see, where do we want to start? Yeah, we're going to start at frame number 20, right? And we have relative sequence numbers off because we want to look at the real sequence numbers. Can I copy that? Value. Let's see how well that pastes. So we'll start with this sequence number, and then we're going to try to figure out how how this stuff works to understand what we want to look at. A few caveats here. TCP is capable of sending data two ways. So I can be sending, the server can be sending data down to the client, and the client can be sending data up to the server. So there's two sets of sequence numbers, right? The sequence numbers the server is using to number its data, and the sequence number the client is using to number its data that it's sending, right? We also have the corresponding two sets of acknowledgement numbers. So there'll be the acknowledgement numbers that the server is sending back to the client to acknowledge the data that the client is sending. And then there's the acknowledgement numbers that the client is sending back to the server to acknowledge the data that the server is sending. So be aware that that exists and that's how it works. But we are going to be looking at one-way data transfer. So we're going to be looking at one set of sequence numbers and one set of acknowledgement numbers. The sequence numbers we will be looking at will be the sequence numbers that the server is using to number its data, and the acknowledgement numbers we'll be looking at are the acknowledgement numbers that the client is using to acknowledge to the server what data it expects to receive next, because it's a forward acknowledgement, so it's trying to acknowledge what it expects to receive next. So we're going to start at frame 20 in this case, because this is the server sending some data to the client. I have this little fancy chart we're going to use in the lab. Right. So the sequence number is this, right? How many bytes of data are there? There are 1380 bytes of data. So if we add 1380 to that, right, we will get the last byte in the segment, which I don't really want to add that, so I'm going to cheat. It adds for us. Here it says next sequence number. So I've told you that the sequence number is a forward, is used to count the number of bytes. Let me start that sentence over again. The sequence number is used to number the data bytes being transmitted. So if my next sequence number is blah, 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 643, then my last byte in my segment is going to be blah, 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 642, right? So is that right? 287.231. I screwed that up. 231.1264. So make sure you're with me here. If the next sequence number, the next byte of data I'm going to send is 643, then obviously the last byte I had to send was 642. The acknowledgement number, we don't care. We're looking at data that the server is sending to the client. This acknowledgement number would be acknowledging data that the client sent. If we actually look at some of these frames, we're going to see that the acknowledgement number doesn't change, right? 650. Oh, it actually did change there. So no, that was the wrong one. 650. And it changed because the client actually sent some data. So I lied. We're not going to start at 20 because that was a small thing that came across. We're going to start at 54. So let's start at that again. Same reasoning behind what numbers we're getting and why, but we're going to start down here because this is a bigger file that's coming down. And ooh, what the heck was that? That was kind of cool. There we go. This is a bigger file that's coming down, so it'll give us more numbers to look at. So in this case, our next sequence number is 560, so that'll make our last data byte 6559. Again, we don't care about the acknowledgement number. So that was frame 54. Frame 55, if we look at that, our sequence number is 2872316. And our last byte of data is going to be 2872317.939. Right. So we look at this using what we have just learned about sequence numbers and numbering of data. Our first byte is this. Our last byte is 6559. That makes our next byte, right, 6560. And our last byte in this segment is going to be 7939 for our last byte. If you recall what we were talking about, forward acknowledgements. In this case, we don't care about this ACK, but the next frame we're going to look at is going to be the frame from the client acknowledging the data, right? And I'm going to predict, just based on my level of awesomeness, I'm going to predict that the acknowledgement number is going to be 17940. So I predict the acknowledgement number is going to be 28723179440. How do I predict that? Am I some sort of, seer of the future? No, I understand how the protocol works. So if we come over here and look at the acknowledgement number, yes, indeed, it is 287237940. So we don't care about the sequence numbers from the client because we're ignoring that. We look at what happens next. Our server sends two, wait, that's not right, right there. Our server sends two more segments. Using my awesome seer of the future ability, I'm going to predict that this is the next sequence number our server is going to send. All right. Look at that, 28723179440. Oh my gosh, I'm magical. And then the next sequence number, I'm going to be lazy. Can I copy that value? I'll paste that in there and then I'll subtract 1 because I'm lazy. So if my next sequence number is going to be 9320, my last byte of data will be 9319. I'll go ahead and put my 9320 there. If I feel like doing math, I could figure out what that was going to be, but I don't. Here I look at my next sequence number. Go ahead and copy that because we're lazy. I mean efficient. All right, 7, so that'd be 699. All right. So at this point, the client's going to send back a acknowledgement saying, hey, yo, I got that data, or more specifically, I'm ready for my next data, and I'm going to predict, again, that that's going to be what it sends because I know so I'm good at predicting. If we look at the acknowledgement number, 287233070. So that's pretty much how we're going to proceed through this portion of this activity, just so we can kind of understand how the sequence numbers work and how the data gets acknowledged, and the acknowledgement number is the data that needs to be sent. So looking at this little few lines of chart I have given you, if you're ever given a chart, and I take some of these numbers out, then you should be able to predict what the number would be if I give you the right numbers. So for example, if I was to delete this number out of the chart and say, what do you think the next sequence number is going to be? Well, you should be able to look at this last data byte sequence number and know that it's going to be one more than that and put, that number back in there. Hey, if this is 6559, then I know this has to be 6560. Same thing down here. If I delete this acknowledgement number, and say, oh, what is the acknowledgement number that the client sent? Well, you should know that the client is going to do a forward acknowledgement, and that's going to make it put the acknowledgement number at 7940, which is what we ended up having. If I delete this number, all right, what is the last byte of data in that segment? Well, the acknowledgement number is one more than the last byte of data, so that should help you be able to calculate that the sequence number, the last byte of data, is going to be one less than the acknowledgement number. Now, could I delete this? That's not what I wanted. Could I delete this number and this number? Well, we needed this number to predict that number, but in this case, we can use this number to predict that, and then, because that's going to be the same thing, right? 28723179440, and then we can then consequently use that number 2317939 to predict that. So yeah, if I give you some of these numbers, then you should be able to use your excellent knowledge of sequence numbers that we have just gained in order to predict what number should go where.